Hi, my name is Zachary Lyons, and this is my video lab report for Physics 2211, Lab 2, the motion of a falling object. In this lab, I'll introduce the system and the surroundings. I will analyze the object's motion as it falls using tracker, starting from rest. Then I will use equations in computational models in Python to predict the object's position versus time. And then I will compare the observed graph with the predicted graphs from Python, and then I'll discuss some key questions relating to this lab. To start, a falling object only has two forces acting on it, which is the force of gravity and the force of air or drag in the opposite direction. These forces are not equivalent, and so there is a net force that leads to a change in the object's velocity. This is shown and explained by Newton's second law, which states that an object that has a net force acting on it has a change in velocity or an acceleration, which is equivalent to the object's mass, the net force acting on the object divided by the mass. The velocity update formula and position update formula shown below were used iteratively in Python and were represented using a computational model to predict the object's position versus time. The forces are described here. The force of gravity is equal to negative mg, and the drag force is equal to negative b, the proportionality constant for the drag force, times the velocity, the instantaneous velocity of the object squared. As shown here in these free body diagrams, to the left, an object has a force of gravity in the negative y direction with air friction or drag force acting opposite to that, but these forces are unbalanced, leading to an acceleration in the negative y direction. However, in the right picture, it is shown to have equal and opposite forces of gravity and drag. This leads the object to reach a terminal velocity or a constant velocity in the negative y direction. The acceleration due to gravity, g, is assumed to be constant at 9.8 meters per second squared, and the drag force is always proportional to the square of the object's velocity. This is the video of the sauce packet being dropped from rest. I chose the axes to be in the negative y direction, so I have a negatively sloped position versus time graph shown to the right. These equations shown prior, the force of gravity, the force of drag, and the update formulas were translated using the starter code in Python, shown to the right. These equations were used iteratively to create the code shown in the next slide. This is an excerpt from the code model without the drag force. So this model will only account for the force of gravity acting in the negative y direction. The sauce packet's mass is shown here to be approximately 0.003 kilograms, and the frame rate of the video was 30 frames per second, so the delta t was 0.033 seconds. The code link is shown below. This is an excerpt of the code where you can see the only force acting on the ball is the weight of the ball, which is shown here. Then the model with the drag force, all of the code is the same, except for the fact that the force of drag is included in the net force, which is equivalent to b times the magnitude of the ball's velocity squared in the positive j hat direction. So these forces are both accounted for. The models are shown here. The orange model shows the object's position versus time without drag, and it is seen to have the most negatively sloping graph since there is no force in the positive direction to counteract the force in the negative direction. So the acceleration here is much greater. Then the green graph is showing the computational model with the drag force. So it is seen to have a much less negative slope, and it is seen to become more linear as time progresses where the velocity is increasing. So the object is getting closer and closer to its terminal velocity. And this computational model most closely matches the data from Tracker, where the objects have very similar sloping graphs. Now, what does this mean? Which model predicts a terminal velocity? The model that predicts the terminal velocity is the model with the drag force. As seen here, the slope of that position versus time graph is becoming more and more linear, which suggests that the object is getting closer and closer to its terminal velocity or its constant velocity in the negative y direction. That is shown to be very, very similar to the actual motion of the sauce packet as it is falling from rest. Now, if the object was thrown horizontally downwards, would anything be affected? The object's terminal velocity is being reached and is only affected by the object's instantaneous velocity. So the initial velocity of the object will really have no effect on the ball in these models. So the graph's slope will not change. These graphs will not necessarily be affected by the sauce packet having some initial velocity. Thank you for your time.